So next speaker is Kagawa from Beacon. He's going to talk about current-induced viscoelastic topological unwinding of Skyrmion space.
Thank you, Chairman. First of all, I'd like to thank the organizers who invited me here. Today, I'm going to speak about our latest results, current-induced viscoelastic topological unwinding of Metastable Skyrmion streams, which is discussed in this paper. So here I have some of my collaborators. Key player of this project is Dr. Ooi, who is a member of my group. And we are also collaborating with the Newton guys. The key player of Newton experiment is Dr. Nakata. This is outline of my talk. As an introduction, I'd like to briefly overview the thermal printing and metastable state because this is the central concept of our study. Then I will move on to the Skyrmion issue. A famous example of the application of thermal printing is probably liquid. So when slowly cooled, all simple liquids turns into a stable crystalline state. But when rapidly cooled, this first order crystallization function can be kinetically avoided. As a result, metastable glassy state is realized. But please note that this glass state does not appear in thermal fusion phase diagram. So we may say that glass is a kind of fusion state. This is another example. This is temperature pressure phase diagram of carbon fabrications. So as you know, the most stable form at room temperature and ambient pressure is chloride, whereas diamond is a stable state at high temperatures and high pressures. So when natural diamond blown in the mantle slowly goes to the surface of gas, diamond turns into more stable graphite state through this first order structure phase function. But when diamond quickly goes to the surface of gas, this first order structural function can be kinetically avoided. So as a result, natural diamond can persist as a metastable state even at room temperature and ambient pressure. So such a cooling rate limit situation can be summarized like this. The point is, for example, all simple liquids can turn into both crystal and glass as long as cooling rate is appropriately controlled. So this critical cooling rate separating the slow cooling regime and the frequency regime varies by more than 16 orders of magnitude from liquid to liquid. And also we can define a critical cooling rate for the diamond to graphite transition. The point is, when the experimental cooling rate is lower than the critical cooling rate, the low temperature state coincides with the thermal equilibrium phase diagram. This is quite normal situation. But when experimental cooling rate is higher than the critical cooling rate, the low temperature state results in some metastable state. So we are now extending this idea to various functional materials. So this is our old example. The target material was an organic conductor. Typical strongly correlated electron systems. And this is temperature variance sensitivity. Here I'm not going into the details, but the point is when rapidly cooled, this charge ordering transition can be kinetically avoided like this. So our systematic studies reveal that in these three structural strongly correlated electron systems, charge ordering transition can be kinetically avoided. Although critical cooling rate depends on material like this. So we believe the concept of the critical cooling rate is universal and can be applied to any first order transition system. So we started to consider the application of thermal printing to bulky 20 materials. This is phase diagram system. So once Skyrmion lattice becomes thermodynamically stable, it is immediately replaced by the canonical phase. Although Skyrmion lattice is a topologically protected non-range order. So I was wondering why. So when we started to work on the Skyrmion issue, it is known that in some limited systems, Skyrmion lattice can be super cool example, in manganese silicide, Skyrmion can be quenched under pressure, whereas somehow it is impossible at ambient pressure. At that time, a lot of experimental cooling rates did not attract much attention. But our idea is that it is an issue of the critical cooling rate and the experimental cooling rates. So namely, we imagine this kind of situation. So for example, in the case of manganese silicide under pressure, standard experimental cooling rate is located above the critical cooling rate, whereas standard cooling rate is located below the critical cooling rate for the manganese silicide at ambient pressure. So this means when the experiment was done and is done under standard cooling rate, the Skyrmion lattice can be quenched for under pressure, but it is not possible for manganese silicide at ambient pressure. So, in other words, our working hypothesis is that Skyrmion lattice can be quenched for all materials as long as cooling rate is sufficiently high, as all liquids can be quenched. To address this issue, we have to control the experimental cooling rate in a wide range. For this purpose, we used this simple procedure. So in the initial stage, sample is in equilibrium with called sample bus. Then, if you apply the strong electric or optical pulse to the sample temperature is rapidly heated up. Then, after the pulse ends, rapid heat dissipation happens because of the large thermal gradient between the sample and the sample bus. So, as a result, rapid cooling is achieved. So, this is the actual data of the rapid heating. So, here we apply the electric pulse to manganese silicide at 10 Kelvin. So, from the time profile of this technique, we could estimate the experimental cooling rate. So, in this case, it is 700 Kelvin per second, which is 4 orders of magnitude higher than the standard experimental cooling rate, which is several Kelvin per minute. So, we apply this technique to manganese silicide. This is the magnetic field versus conductivity at 10 K. So, the graph data is corresponds to the equilibrium condition. So, as you see, in this condition, the normal Hall effect and the abnormal Hall effect are negative small. Then we apply the electric pulse and the sample temperature is rapidly heated up and then cool down. As a result, large topological Hall effect appears. So when we decrease or increase the magnetic field from this point, we found that the lower X remains enhanced in some field range, and then sharply drops to previous value. So this observation indicates that Skyrmion lattice is quenched as a result of rapid cooling. Later on, this conclusion was directly confirmed by measuring the mean of strategy experiment. So we also investigated the cooling dependence of topological electricity after the rapid cooling. So as you see, this is the cooling rate profile. Cooling rate versus as you see, large topological Hall effect appears only when experimental cooling rates exceed several tens Kelvin per second. So this observation indicates that experimental cooling rate is a key phase control parameter for Skyrmion lattice, as in the case of Witt and Dyson. And we did similar experiments at various temperatures and constructed the phase diagram before quenching and after quenching. So here, two things can be highlighted. The first, metastable Skyrmion lattice is quite expensive compared with the previous Skyrmion lattice. And second, there is an appreciable temperature gap between previous Skyrmion lattice and the quenching Skyrmion lattice. So this temperature gap is because the lifetime of metastable Skyrmion lattice is short in this intermediate temperature range. So this is the reason why we need the very rapid cooling. So if the sample slowly passes through this intermediate temperature range, the metastable Skyrmion lattice immediately turns into more stable chemical state. So here, important questions may arise, such as what is interesting about quenched metastable Skyrmion lattice, and is it a simple expanded of the basis? I think these questions are very important. So far, fortunately, several new topics which are difficult to be addressed we found possible new magnetic structure within the metastable triangle SkyrMion state in magnetic working pattern. So the point is, this WQ diffraction pattern is not observed in some equilibrium condition. So this state should be for a hidden state. So this state may be related with some sphere standards proposed by some organizers. And then this hidden state can be understood from a somewhat dynamic point of view. A hidden state can be understood as following. This is the hypothetical temperature dependence of reagents for three phases A, B, C. Suppose A is triangle phase, B is conical phase, C is some hidden state. When slowly cooled, triangular SkyrMion lattice comes into conical state through this first order phase function, and the C phase is never here. So this is the reason why I call C phase a hidden state. But when rapidly cooled, this first order transition can be kinetically avoided. As a result, triangular SkyrMion lattice can be supercooled to a low temperature. So then there might be a chance to undergo another phase transition as long as hidden state has lower free energy at low temperature. So as seen in this example, quenched metastable state may generally be a promising loop to explore a hidden electronic or magnetic state. This is also the main subject in the field of photo-induced phase change. Another example of the merit of quenched SkyrMion lattice is that we could perform an unconventional phase control. This is the working principle. So starting from the equilibrium conical state at low temperatures, then if we apply the electron pulse, the sample temperature is radically heated up and left equilibrium, then we can get that quenched SkyrMion. Then when starting from the quenched SkyrMion lattice, and when if we apply the relatively long and the relatively weak electric pulse, the sample temperature is heated up to this intermediate temperature. So in this temperature range, quenched steam configuration can easily relax into more stable steam configuration. That is conical state. So this is the working principle. In fact, we could demonstrate the reversible and non-volatile switching between quenched SkyrMion lattice and equilibrium conical state by applying a pulse, electric pulse. This is what scientifically confirmed with always stated topological measurement and also experiment. So this is a different approach from the standard phase control using pressure, strain, something. So with this technique, we could also perform a very primitive domain engineering, which was very important to study the next topic, current-induced viscoelastic or metastable SkyrMion strings. So please note that we are studying a metastable SkyrMion string lattice. So this means a complex string-like trivial freedom may be involved in the SkyrMion dynamics. So we did experiment at 10K and 15K, which is much lower than the equilibrium SkyrMion lattice. So first we try to write the metastable SkyrMion lattice in an area selective map. This is our experimental setup. Here we can prepare the high contact resistance electrode at the surface of the sample, which enables efficient Joule heating. If we apply the efficient local Joule heating, so if we apply the electric pulse to the left side electrode, the sample temperature of the left side is rapidly heated up and then cooled down. As a result, cortical core effect appears only in the left side, whereas the right side is silent, and vice versa. So these observations indicate that we could write the metastable SkyrMion lattice in an area selective map. So with this success, we could study whether metastable SkyrMion string lattice can be transferred from left side to right side. The answer is unfortunately no. We found that the quenched SkyrMion lattice is destroyed by organic current rather than being transferred. Let me discuss this issue in more detail. So originally we we have expected this kind of data. So when we apply the in-plane current pulse, the written topological coordinate to the left side, it appears like this, and eventually the signal is transferred to the right side according to the Skyrmion motion. But this was not the case in our experiment. This is in-plane pulse number dependence dependent versus topological coordinates measure at the left side and the right side. So as you see, when we apply the in-plane current pulse, the topological pole effect, topological pole signal immediately starts to decrease, right? And then nevertheless, no signal is transported to the right side. We also tested the alternating application of positive and negative in-plane pulse, so which is represented by plus/minus here. But we found in this case the topological pole effect decreases more pronounced. So, a straightforward interpretation of these observations is that Skyrmion strings are destroyed without being transported. So, when considering the destruction of Skyrmion strings, topological defects such as emergent magnetic monopoles is likely to play a key role, as discussed in this video. So, in the destruction process, one has to consider the creation of new monopole anti-monopole pairs and their unwinding process. These two processes qualitatively correspond to new creation and growth process in the standard process. To gain insights into this issue, it is helpful to consider the magnitude of the involved current. According to the theory, the monopole anti-monopole pair creation requires large current density such as 10 to 12 ampere per square meter. But in our case, Skyrmion string destruction starts to occur at this 10 to 6 ampere per square meter. So this large difference indicates that current-induced creation of magnetic monopole anti-monopole pair is highly unlikely. The remaining possibility is that monopole anti-monopole pair exists from the beginning, and their unwinding process plays a key role in the destruction. So, in fact, numerical simulation shows that the creation energy of monopole anti-monopole pair is only 200 Kelvin per system. So, one should expect the monopole anti-monopole pairs over finite density at finite temperature. In the simplest calculation, the mean distance between pairs is estimated to be 4.7 micrometer for magnetic side in the thermal Hilbert space, whereas the thickness is about 100 micrometers. So this means each Skyrmion string is expected to contain about 100 topological units. So this situation is analogous to the fact that ordinary crystals at finite temperature contains vacancies of the finite density at equilibrium. As you see, free energy minima is located at finite density vacancies as a result of competition between energy penalty and configurational entropy gain. So, but on the other hand, we have noticed that our critical current density for the Skyrmion destruction is quite close to the reported critical current density for the Skyrmion motion in performance system. So, a natural question arising here is what is the possible link between Skyrmion motion and metastable Skyrmion destruction? To gain insight into this issue, we have asked our theorist colleagues, Dr. Koshibaya and Professor Nanaosa, to numerically simulate the current-induced dynamics of the segmented Skyrmion strings under the influence field. In fact, they found that even if metastable Skyrmion strings is segmented like this, but this structure can still remain metastable because of the help of field potential. Then they apply in-plane current like this, and pinning of the in-place Skyrmion motion triggers the monopole motion along the direction. The reason is that Skyrmion strings can be pinned at artery in-place, almost artery in-place position, whereas the monopole cannot be pinned at arbitrary position. Probably because Skyrmion string tension is always present because we are considering metastable Skyrmion strings. So as a result, the pinning for the in-place Skyrmion motion also triggers monopole motion. So to the first approximation, monopole velocity is dominated by the Skyrmion string tension, in other words, metastability, whereas the Skyrmion drift velocity is of course dominated by So in the last topic, I will discuss the viscoelastic nature of the current-induced topological unwinding. So viscoelastic nature means that a system may behave either a fluid or an elastic solid, depending on your time. These are examples. So water is of course fluid, but if you throw a small stone appropriately, a small stone can bounce as if water and elastic solid. This is another example of so-called Viscoelastic experiment. This highly viscous asphalt is drifting off like a fluid, but this is typically 1 part in here. But you can smash it like a solid. So as seen in this example, in many materials, fluid nature and elastic nature can coexist. This is also the case in the domain of motion. This is the ferroelectric domain of motion using the dielectric spectroscopy. Here, the sweeping parameter is frequency. This figure shows that at high frequencies, domain walls remain pinned and exhibit a reversible motion, like one elastic solid. But at lower frequencies, domain wall starts to be pinned and exhibits reversible motion, like a fluid. This is a viscoelastic nature seen in the frequency. So the point is, the critical frequency spike in the pin regime and pitch regime depends on the strength of the electric field. Conversely, if we consider the domain of the pinning under the pulse applications, in that case, the critical electric field depends on the pulse use. So how was the case of Wisconsin? To address this issue, we have investigated the pulse use dependence. So here, the main pulse number was written topological. So as you see, for the non-pulse applications, topological unwinding occurs very pronouncedly. But in the case of short pulse application, short pulse width application, topological unwinding is much less pronounced. So please note that the least topological unwinding for the 5 millisecond pulse application is not because the integrated pulse width is the shortest. So in fact, if we plot the same data as a function of integrated pulse width, then we found that the short pulse application still exhibits the least topological unwinding. So this means the short pulse width is intrinsically ineffective for influencing the beam. In other words, large current is needed for the case of short pulse. So we measure the unwound fraction after 200 pulses applications, so as a function of various current density and various pulse widths. So from this figure, we would like to extract the pulse width dependent critical current density as a hallmark of viscoelastic nature. But as you see in this figure, the threshold is not so clear. We found that this data set obeys some parallel behavior like this. So the parallel behavior means that critical current density is there in the balance. This may sound strange, but consistent with, I think, consistent with the notion of Skyrmion motion. So as long as temperature is finite, the pin elastic object can pop to the neighboring side with a finite probability of current. So nevertheless, we can still define graphical and critical current density about which we can identify the Skyrmion motion or Skyrmion structure. So here, in this case, we define the graphical critical current density as the current required then in this way we could extract the pulses dependence of the critical current density at 10K and 15K. So as you see, critical current density is pulses dependent, which is a hallmark of this classification. And we also found the dependence can be described by power of the exponent of 4.5 or 4.6. So unfortunately, currently we are not able of qualitatively explaining this critical exponent, but probably the exponent is likely to be linked with the microscopic internal information prior to discovery. In fact, in the field of charge density effect, the meaning of the exponent for the being is discussed by comparing the experimental and theoretical reaction values. But unfortunately, probably there is no theoretical prediction to be compared. So, okay, let me summarize. Let me summarize my talk. I have introduced the concept of critical period to quantum materials. Then we applied this concept to the infinity materials, and with the use of some reference Skyrmion practice, we explored the hidden magnetic state and designed the non-diamagnetic example by using pulse, and also we did very primitive domain writing. And we also found that the meaning for the impedance combination triggers the destruction of metastable strings. Probably some reactivity dependent magnetic models play a key role in this process. So obviously, if we use the much thinner monopole samples, the Skyrmion transportation will be more successful. And we have also discussed this process. Thank you very much.
Thanks also again for being here on time.
Question concerning this monopole. So I guess the question is first whether you believe that the monopoles are already present in the thermodynamic state phase before you quench.
Yeah.
And then would it not be possible to anneal somehow the Skyrmion phase to get rid of the monopoles, say by shaking or something, so that you get rid of the monopoles and then you would get a sufficient signal?
And is lower than the cubic value? Lower than the some cubic value? I think.
Yes, well, I mean, you have some Arrhenius kind of law which determines the density of monopoles, but I could imagine that nevertheless you can get rid of these monopoles. These are like defects in the crystal, so you could get rid of these defects by some sort of annealing.
That's a very interesting idea, but sorry, we haven't tried such kind of experiment. But I imagine it is difficult to achieve the lower value than the expected equilibrium value. But in some cases, probably the density of monopole is higher than the expected equilibrium value. So in that case, by some annealing process, we can reduce the density of monopole to the equilibrium value. But we haven't tested.
Well, I mean, so if it's in order to try to move them, then of course it's a problem that if you move them, they get destroyed. But if one imagine doing the opposite, that rather than writing Skyrmions, in the conical background, you could try to write conical domain in the Skyrmion background. Then you get around the problem.
I see.
So basically, if you can make a metastable lack of Skyrmions.
So you are mentioning the writing of conical phase in the matrix of Skyrmion. I see. That's also an interesting idea. Yeah. Currently, we haven't tried such things, but so as long as thermal quenching is considered, it is possible to quench the high temperature state to a low temperature state. But your proposal like this, I see.
very related question to the notion of this monopole. Now, of course, if you have this metastable state with a monopole, and then it likes to be alienated, so you need some local defect to pin this here.
Yes.
Now, of course, depending on the system, you might have these bobbers, which can be stable. Have you thought about moving these bobbers? Because then they are, because they are in half the DMI period, so they're happy to be a certain depth.
I see. That might be possible. But sorry, in our case, we are measuring the bulk.
Yeah.
Topological depth, so it's difficult to detect such whether the boba is the one. But I think the boba is possible.
Also to get information how far this Skyrmion crystal shoots, in other words, how far it goes before it disappears from the region of the
Yeah, experimentally we have no information. We have just tried this experiment setup. So we are measuring the topological effect only 2 positions at the distance of 1.5. So if you put many electrodes, we can reduce some deviation, big scale of the Skyrmion lattice transformation. But currently we have only this experiment, so it's difficult to do. So at least we can say that no Skyrmion lattice is transported to this kind of distant position.
What is the weak current? So the strong current is 100 milliamps, the weak current is?
10 to 5th detection for detection. Yeah, 10 to 4th or 5th ampere pascal.
But that's all affected 100 lower.
100 lower than the
Yeah. Okay. I think I already know this one. Maybe.
In the supercooling of the Skyrmion phase, I do not understand why always supercool the Skyrmion phase and you do not supercool the liquid, the parameter. Now, I would expect in your experiments you supercool just the parameter, but you always enlarge the Skyrmion. This is unclear. Why is it? So in your phase, if you go to your phase diagram and you compare with this enlarged supercooled Skyrmion.
Yes.
So obviously, always if you do your range experiments at 10 Kelvin, you find this range Skyrmion. But why can't you supercool just the paramagnet? That's the liquid. But for me, it would be naturally to supercool the liquid.
Yeah.
Why not? So why does the Skyrmion?
Yeah. To be honest with you, we have really expected such things because, in fact, in our experiment, the temperature is heated up to permanent.
Yeah.
So there is two parts of the structure here and here. So one possibility is that paramagnetic state can be traced to the lowest temperature. But we found that it's not the case in our experiment. So that means critical accumulate to avoid this paramagnetic to Skyrmion structure is much higher than the critical accumulate for the Skyrmion to conical structure. So
What happens if you go here? You do the same experiment here.
in that case, no
You
so no topological folder here. You see.
Okay, we don't know if you are end up with conical or with cubic. You go like this. Do you know if you are conical or cubic?
So in terms of orbit sticking nature, probably in this case, probably simple feedback. So maybe feedback accumulate is largely divided between these two fields.
So I think there's one question by our organizer and then we might have to.
So do you have a chance to measure the topological effect in the Skyrmion lattice in terms of the frequency and function of the function rate? You know, when you do the fast function, so basically the Skyrmion lattice will not have sufficient time to form a perfect lattice. As a consequence, you will be plenty of topological effect in the Skyrmion lattice.
By some specificity.
Yeah, for example, maybe you can see this from the from
may include some density of topological defects. But sorry, we haven't done some systematic investigation of the primitive values of this. But this may include information.
So I think we had a lot of time for discussion now over the break. So we'll reconvene in half an hour. Please join me in all the speakers of the session.
So if you want to share the chat box, we are